This is FM synthesis. So in the interactive teaching session, we've done just that. We've been creating an FM synth in a step-by-step manner. FM synthesis, frequency modulation synthesis, is a form of sound synthesis that is based on two oscillators controlling each other. The one oscillator is called the modulator, and the other one is called the carrier. Most often, modulator and carrier are also combined with a VCA and an EG. Now, with FM synthesis, you can create both harmonic and inharmonic sounds. In order to create harmonic sounds, the modulating signal must have an harmonic relationship to the original carrier signal. That means that the frequency of the modulator should be in an harmonic relationship to the frequency of the carrier, and this can be established by having full numbers, integer number relationships, so 1 to 2 or 2 to 3 or 1 to 4, stuff like that. Through the use of the modulators, when we have non-integer multiples of the carrier, we get inharmonic sounds, and they quite often sound like bells or percussives. So we can generate both things, more harmonic or more inharmonic sounds. Even though we are only using two sine oscillators, the amount of the frequency modulation controls the complexity of the sound that is generated. So we can create really complex sounds with only these two operators. Now, while the principle is very simple, it still took some time to actually understand this kind of principle. And John Chowning, who is displayed here, of the Stanford University, has developed the FM synthesis in 1967, and it became very, very successful as it was licensed to Yamaha and is the basis of the very successful DX7 synthesizer, a digital synthesizer that is based on the algorithms, the FM algorithms that Chowning has developed. Now, these kind of algorithms inside the DX7 can be depicted in kind of like block diagrams that we see here, which are printed on the device itself. So the DX7 at that time had 6 sine operators, and a sine operator, as I mentioned before, is more than just an oscillator. It can be viewed as a package containing the oscillator, an amplifier, and an envelope generators, and these operators can be combined and can take the role of either the carrier or the modulator. By arranging the operators, we can generate harmonically rich tones, as we've explained early on. And the DX7 knows so-called 32 algorithms. And these 32 algorithms are displayed here. And in order to have an understanding what is going on, they are stacked on top of each other in a vertical manner, and it should be noted that if they are stacked vertically, then the higher operators are modulators, and the lower ones that are on the lowest base here, on the lowest line, these are the sound generating carriers. So we've got 1, 3, 1, 3 carriers here, and we've got 2, 4, 5, and 6 modulators. So, and this is basically the architecture of the modulation scheme, and one that is very easy to understand would be the very last one. As you can see, we don't have any vertically stacked modulators, so these are just sine waves which will be added together. So algorithm number 32 is just additive synthesis, of which we have spoken before. All right, now in order to put this into SuperCollider, we can do it in a way that we show here. That's a very simple FM synthesis that we have developed within the course. And you can see we've got a modulator here in line 11, and we've got a carrier. And the modulator is added to the frequency value of the carrier. So FM synthesis is based on adding the modulator to the frequency value. phase is 0, multiplication is 1, and then we see we've got the mod amount. This is the how intensive, how loud the modulator is, and the louder it is, the more complex the signal is going to be. And then we've got two factors, the C factor, which is the carrier factor, and the modulator factor. Here we can basically just send or hand over any number, and if we've got integer values here and we've got an integer relation, then we get harmonic sounds, and if we have a non-integer relation between these two factors, we get inharmonic sounds. So in addition, there's also an envelope. In this case, we've chosen an ADSR, and the envelope is just controlling the volume of the overall signal. And then there's an amplitude parameter that basically controls the main loudness. Using the PAN2 UGen, we are placing the signal within the stereo field. Okay, in this case, in the middle. So we get a stereo output here. Now, while this is working and it's really sounding very nice, it's still not quite the same that we find here with this approach and this approach, because usually you have another factor which is called the index. And the index is defined to be the relation between the mod amount and the mod frequency. And index is a number, and this number loosely corresponds to the amount of spectra we are going to generate, or sidebands that we are generating. So this is the revised version of the FM synthesizer, and you can see we've now got another argument which is called index. Usually it's 1, and we also only are using the MFAC and CFAC for the modulator by simply dividing these two together, which simply means that here the C factor is going to be 1 and it can't be seen. So that simplifies the stuff and also allows for the fact that the carrier is actually taking the frequency that we are handing over. So it's running at 200 and not at 400, 500 and 600 or anything like that. So, and as you can see, we now have FRAC times MFAC divided by CFAC, and we also have as the mod amount FRAC times MFAC divided by CFAC. So this part is equal to this part. So basically these two numbers are the same. So in other words, the amount of sidebands is simply controlled by the index. All right. The rest stays the same, so we're just using the index here, and the rest stays the same. So that's the synthesizer that allows us to use the index as a number of complexity. And down here we instantiate one of the versions. Now, in order to check that out, I implemented a MIDI control, which is not really interesting, but because it's always the very same thing, we're just using node on and node off events, and we're again using an array with 120 fields. And then we've got a number of fields, a number of variables that simply store the state of the synthesizer, and they are going to be handed over to the synth instantiation. And by checking for control changes, we are just kind of like using a certain knob. In this case, on my Arturia Minilab Amp Mark II, a certain knob that can be turned and will give MIDI values between 0 and 127. And then we basically just map the value to appropriate values for mod amount, for MFAC, MFAC fine, and stuff like that. All right, so this kind of structure is very similar for basically all synths or all interactive instruments that we are going to build. So you may keep this as a template for just connecting it to your own MIDI device. All right, there's one thing missing though in the FM synthesis, and we haven't really implemented it, but we can see it here on the algorithms. That is, the data flow goes from top down, top to the lower levels, but we also have this self modification, this self reference here, recursive reference. Now the problem is, in order to implement this in SuperCollider, we can't just basically enter the left side here. So we can't say sine osc.rr frequency plus mod. So we are just kind of like having a reference to ourselves. This doesn't work out, and you get syntax errors then. So the way of really doing these kind of feedbacks is to use a so-called local bus, and we've got two local bus which we can define, or two UGens that are referring to the local bus, better to say, and the one is local in and the one is local out. And local in basically says, okay, use the signal that you are currently using here, so do a feedback, do a loop, and with local out you basically define this is going to be the signal that can be fed back into ourselves. And as you can see, we are saying local out is mod, and therefore local in here is mod also. So there's the relation between, and so we are feeding ourselves back in. Now the parameters for local in is, the first is the number of channels. So in this one is a single channel, a single channel bus. All right, and these of course can then be controlled, for example, by the mouse. So line 52 and 53 are basically implementing a line like that, Please note that there's only, because you could only use one local in and one local out within a syndev, so you have to combine all the signals that you feedback in. As you can see, I commented out the carrier, so in this case I'm only displaying the modulator. And then when you do this and you'll have a look at the frequency, you will see that there is a high amount of DC within the signal, and in order to filter that out, you're just using the leak DC RR, which is going to just remove that. So, when you will see this kind of DC amount on the very lowest part of the frequency spectrum. There's a high value, which you can see, very stable high value. Okay, so this is how you do feedback within SuperCollider and use it. So you may try it out to extend this FM synth to add also to add feedback within this stuff. All right. So let's have a short listen to a simple recording. Nothing very special. Again, just a sequencer. That I've implemented on the Arturia, but we can't really hear it right now. Oh, I see. Okay, you will be able to hear it, but I'm just not hearing it because of the speaker that has been turned off. All right, as I said, nothing special, but we can hear chords, we hear bass, we hear filters and stuff like that. Okay, continue with the conclusion. FM synthesis is built by modulating the frequency of a carrier signal with a modulator. And the timbre that we can see is controlled by the harmonic-inharmonic relation between the modular and carrier frequency, and by the index. And this index controls the numbers and intensity of the overtones. It also is controlled by the envelope generators controlling the modulator and the carrier, which we actually haven't shown here. And also by self-modulating of the modulator, which we've seen with the feedback. Okay, so far the little unit for FM synthesis.